So hi everyone, welcome to the data science seminar. It is a great pleasure to introduce Dr. Tolga Birdal. He is an assistant professor in the Department of Computing of Imperial College London. Previously was a senior postdoctoral research fellow at Stanford University within the geometric computing group of Professor Leonidas Gibas. He received his master's and PhD degree in computer science from the Technical University of Munich, and he was mentored by Professor Nasir Nawab. He was also a doctorand at Siemens AG under supervision of Dr. Soloban Illig, working on geometric methods for 3D reconstruction from large point clouds. His current interests include geometric machine learning and 3D computer vision. Aside from his academic life, Tolga has co-founded multiple companies, including BeFunky, a widely used web-based image editing platform. And he's going to talk about probabilistic inference on manifolds using diffusion models and its application in 3D vision.
Yeah, thanks, Gilad. Thanks for introducing me. And I am ready to go whenever you feel like.
Oh yeah, go ahead. Yeah.
Okay, cool, great. It's a pleasure to be here. I should say, when I think Gilad and his collaborators and students had some kind of a related work to some of the topics that I've been working on, mostly synchronization, and I will be touching on these topics also. But I wanted to give fundamentals into how I approached this in the beginning, and then I will move on to the applications. So part of this, I actually prepared as a course at Stanford. So it was called Non-Euclidean Machine Learning and included some other stuff. But I'm really thinking that fundamentals in machine learning already come from some fundamentals in probability and optimization. So I think it's good to dive into those a little bit, and I will actually start by this, right? I will start to see the machine learning problem from a probabilistic lens. Usually, we are given some data, right, D here, and some labels, Y. It's a very typical supervised learning problem, and we architect a model called F and parameterize it through theta. It's general optimization. You can fit the deep learning into this framework as well, and then we run some kind of an optimization to figure out the parameters of F, which are theta. And if you do this on a previously available data, this is called training. If you do this during test time on a few samples, this is called either optimization or, depending on the context, inference. Right, and most of the time, just having these models are not enough. We try to come up with some regularizers on the set of parameters that we are looking for. Right, so we have these data terms and regularization terms in our energy, and we construct this minimization to figure out what the best data would be. Now, if you see it through a probabilistic lens, this immediately reveals itself as a likelihood term and a prior term. So the likelihood, of course, we don't have a real probabilistic model in this context, but you can think this through a Boltzmann or Gibbs type of distribution, where we first write down the energy function and then consider basically the probability distribution induced by the energy. And of course, likewise, the priors are related to the choice of the regularizers. So depending on what type of a person you are, you would first write down either the minimization or the probabilistic view. But essentially, they are almost the same, right? And of course, under this perspective, the above minimization corresponds to a log maximization, and or you know, of a combined likelihood and prior, which, as you know, is related to the posterior distribution. But of course, here we have a term missing, right? It's the normalization term. And usually when we ignore these terms, we are dealing with a maximum a posteriori estimate, right? So this is not true Bayesian inference, if you want. It's but it is very much related to typical optimization problems we solve every day under the guidance of a regularizer. Now, in the Bayesian sense, of course, this is proportional to the posterior, and physics people also, you know, call this likelihood term a potential energy, or the objective function, or data term is a potential energy, and that is a combination of this likelihood and prior, right? And characterizes the energy landscape that we are operating on. Now, as I said, there's a little bit of a nuisance, as you all know, right? It's an integral in this equation that I cannot ignore. So arguably, Bayesian inference is hard because this is hard, right? So how can we get around this problem? You know, this is all very well known until this point. You basically draw samples from such a general posterior by using certain techniques like Markov chain Monte Carlo. Okay. And, you know, please interrupt me. I think if you write down things in the chat, Gilad will be able to read them to me, and I can respond to the questions. And if anything is not clear, please interrupt. Right, I am not going to get into the details of this. Of course, you all know Monte Carlo, you know, some basically just coming up with random hypotheses and trying to verify them, you know, verify whether those hypotheses would solve your problem or not. So Markov chain Monte Carlo is a little more interesting. It's basically you are trying to ensure that the samples you draw are actually coming from a probability distribution that you desire. And for that, you construct a chain. So you draw x0 from certain probability distribution and then transition this distribution such that it would cover your next sample x1, and then, you know, x2, x3, you go on like this. And at some point, you converge to a probability distribution, you know, which remains identical almost, or people call it invariant. And your samples are explained by this probability distribution. And people have proposed a lot of things, MH, Gibbs samplers, right? And they have been found to be ineffective. That's one thing. But, you know, I'm not really a Monte Carlo researcher. So for me, the more important aspect is that they are not super geometrically motivated. So I will be in this talk looking for more geometrically motivated algorithms to do that. And Hamiltonian Monte Carlo actually is one way to achieve this. So in it, let's assume for a moment that our variables theta are coming from a Gaussian distribution, and allow me to introduce this momentum or m, another variable m, which I will later call momentum. But let's just say I have this variable m right now as well. And then I will consider the joint distribution of m and theta. Okay, and you know, physics people came up with these things, obviously, and they have named it the phase space, for example. And now I have this because they are coming from this Gaussian, the phase space is taking the shape of Gaussian contours, as you see here. And I can do something interesting in this setup to draw samples from this, you know, in this case, the joint posterior. I can do something interesting. I know that all these lines you see here have an identical PDF. So they are isolines, if you want. And if I can just draw a sample randomly and trace that curve, right? I can sample all the points along that curve, and I don't need any sampling within the curve again. Well, I do need sampling, but you know, it's pretty much determined given a random point. So if I know how to trace them, you know, I can do something interesting. So to do that, let me just take the log of this joint distribution. Okay. And then let me rename these things. So I will name the log P as H, and that will be an Hamiltonian. And this, the second term, I will name it as the potential energy, basically. And the third term will be the kinetic energy. Like, this is just physics correspondence, but you see what's going on here. Anyway, it's a joint distribution. We just took the log. And you can immediately see the connection, of course, to the previous scenario, but I will come to that later. Now, if I write this a little more openly, you know, Hamiltonian is nothing but the joint distribution almost, and you know, it's composed of potential and kinetic terms. And kinetic term here, you can even see like it looks like a regularizer. Good. And since we are in the Euclidean space, in our variables, I will call this like the Euclidean Hamiltonian. So coming back to, you know, just let's take a note of this. Coming back to the idea of tracing curves, where I know how to trace those curves. These are simple, you know, differential equation tricks, basically. So I can model the change in individually in theta and m and relate it to the change in the joint posterior, right? And if I solve these equations jointly, I will just be moving around these contours as long as I simulate those equations, right? Well, I know how to do that, but before that, notice that the kinetic energy term is not dependent upon the variables theta. So this partial derivative you see here is actually the gradient of the posterior that I have, right? So suddenly I'm trying to slowly relate MCMC type of stuff or sampling stuff to the gradients of the posterior. And really how we should see this is like the, you know, because potential energy, like the posterior, is related to the or proportional to the negative exponential of this potential energy. So one way to see this is really that I have a ball and I kick this ball with some momentum, and this ball goes deep to this valley, which is characterized by the landscape. And then, you know, there is certain kind of friction maybe, so it keeps coming back to this, or gravity if you want, it keeps coming back to this point. So, you know, if I know how to trace these curves and I know how to simulate those things, then I can do this trick to do the sampling. I can draw a random momentum vector and I can simulate the Hamiltonian dynamics, like these, tracing the curves basically. So it's just hypothesizing a point on this joint landscape and then just tracing the curve. And I can keep doing this for different random points. And in the end, I will have a nice characterization of the landscape. Of course, sometimes during the simulation, I can get out of the curve. So to do this correction, if you want, I can do this Metropolis-Hastings correction, which is nothing but rejecting certain jumps or certain moves. Good. So this part is interesting for this talk, how to simulate these dynamics, right? And I'm sure most of you would know this. Exact simulation is difficult for us. We usually do discretization, right? And there are many discretization schemes, but one obvious discretization is through Euler's method. And now if you consider the previous two differential equations jointly, so I will just go back a few slides. So if you look at these two differential equations, right, and you actually know how to write these things down, you know, in the lens of the energy potentials, right? like basically like the H here. So if I plug the H, this Euclidean Hamiltonian, into this equation, I can compute these derivatives. And they look like this. And if you are a bit familiar with training deep networks, for example, you would immediately see that we have recovered the gradient descent with momentum algorithm just by the discretization of this nice Hamiltonian or curve tracing algorithm. So of course, we don't have any random sampling procedure here. So this is really an optimizer. But if I introduce in some means the random sampling, then I will be relating it to the MCMC very soon. So now you see the connection that there is a relationship between simulating a dynamical system and sampling the posterior somewhat. And people have come up with a more general scheme for doing this, and it's called a dynamics-based MCMC, which involves one way or the other a gradient-related direction about the landscape, plus a random movement. So these two steps that I have been described can actually be simulated in one stochastic differential equation, if you want, which you see here. So if I have no randomness, so there's a diffusion on the right hand side here, which is a Brownian motion, and there's a diffusion matrix D. But if I pick this matrix to be 0, you end up with a drift term. And that drift is just, you know, the typical simulation. If you have the momentum, it will be corresponding to the previous gradient descent with momentum algorithm. But if you don't, and just use the Euler's method to discretize this, it's nothing but a gradient descent, as you see, right? So, you know, there is all this connection going on apparently. So how can we leverage this even further? Of course, for different choices of this diffusion matrix and different choices of descent direction, there will be interesting stuff going on. So one choice is, let me pick this diffusion matrix. Is really like a scalar which is related to the variance. Then I can recover some metropolis adjustment Langevin algorithm, and the adjustment just comes from the fact that we still have this metropolis Hastings sampling going on. But of course, this is a random walk behavior, though it's very useful in practice, especially as I will just briefly mention later. The common diffusion models we use nowadays are very driven by that particular SDE. And people have chosen different things for this D, and you see the reference on the you know here on the left bottom part of the slide is a beautiful paper that says, you know, for if I choose this particular form, so F is like a D plus Q times this gradient of the Hamiltonian plus a lambda, you know, then depending on the choice of D, Q, and lambda, I can recover many different dynamics based MCMC methods. So these are called diffusion curl and correction matrices. And of course, when we don't have the diffusion, we have an Euler discretization, and that gives us a optimizer. Then we have a stochastic differential equation. We use Euler-Maruyama discretization, and it's going to give me some kind of a more stochastic or gradient descent type of an algorithm, or stochastic simulation, if you want. So you see that although these things look big, I mean, they don't mean anything right now. They are just rewriting of this F in terms of, you know, some matrices. One interesting thing is, how can I avoid this correction, right? I don't want to do this all the time. Well, if you assume that the true gradient plus a noise would give me a stochastic gradient, which is a gradient computed in the batch of a data, then people have shown, machine learning people have shown, that you actually don't need to reject much. Of course, this is a very strong assumption. People have been fighting this for some time, and you know, some people say that this never holds in practice, but there are many analyses conducted just by this assumption. Okay. Right. So this is a differential equation. As I said, whose discretization is again going to give me some algorithm, and that's nothing but a Langevin update. Okay. Now we can speak of the special cases. You know, if you choose D, Q, and lambda like this, then it's Hamiltonian Monte Carlo. If you choose it in certain other way, and you know, do something stochastic, then it's going to be stochastic gradients and stochastic gradient Langevin dynamics, and so on. So for me, something else is interesting today, and that is particularly the you know, data in non-Euclidean domains. So for that, because you know, this is actually the data that that I work with every day. You all, you know, these things you see here are geometrically and topologically very interesting. And of course, these methods are not very applicable because of the non-Euclidean structure of this data. So I will give you a very brief overview. I cannot cover the whole subject, but many of the probability measures that we see, you know, the definition of probability basically relies upon the choice of a measure. So the choice of a length, if you want. And that length in the Euclidean case is very simple to choose. It's called a Lebesgue measure, right? It's either the length or the area, depending on the dimension or the volume. Now, when you go to manifolds, which live in lower dimensional subspaces of certain ambient space, which is usually taken to be a Euclidean space, the Lebesgue measure doesn't work anymore because it simply vanishes. So we will instead have something else. But let me look at the, you know, just give you a very brief overview of, you know, how we can think of this whole scenario. Is basically, we have an ambient space called M. This could well be Euclidean. And then we have a submanifold N, which is embedded in M. Now, to any point Q on N, I can assign a chart, you know, which is a Euclidean space, because the manifold is locally Euclidean looking. And of course, I can define a parameterization or its inverse, the chart between this Rm, which is M is smaller dimensional, and N. You can also alternatively consider another embedding, which goes from N or M to this, well, to what you see on the right here, to this point X, from Q to X, with psi, right, with the map psi. And then, of course, this Rn can be, you know, here three-dimensional also. And now you can actually use the inverse of this mapping embedding function, or you can use the embedding function and the inverse of the chart to relate these two directions. You already see that there are two paths going from Q to X. Well, through this lens, you can actually write down the Riemannian metric associated to this, you know, point in the embedded space, right? And then the relation, well, just let's ignore this part. The relation between, you know, to basically to define the probability distribution, what we need, the relationship between a Lebesgue measure and the measure of such a configuration. And that's given usually by the Hausdorff measure. And the relationship, I'm not going to write down the entire thing because it's rather complicated, but the relationship between a Hausdorff measure and Lebesgue measure is given by the determinant, right? And it's basically the deformation of the volume, right? So it's a volume measure in the end. So if you want to go from one manifold to a Euclidean embedding, you basically need to correct for the measure proportional to the determinant of the gradient, so determinant of the metric. So, okay. And through this, you know, just because now, you know how these two things relate, you can actually use change of variables to define integrals on the manifold, right? And you solve these integrals actually in the embedded space, okay? And then just because you can define integrals, you can start speaking about probability distributions, of course, that are defined on the manifold, as you see on the right. So let us also relate all this Riemannian notion to the Hamiltonian we have seen before. I had two differential equations here, right? And now you remember this matrix M, which was called the mass matrix, and that was a term in the kinetic energy. And the derivative with respect, well, the derivative of theta, the parameter, was given as this M inverse M with respect to M, of course, because the potential energy. So you see that on the left hand side, there's the derivative of theta and the derivative of H, the Hamiltonian, with respect to M. So that is only a function of the kinetic energy. And if you take the derivative, you end up with this one. And that's just the theta, theta prime. Now, if you define the inner product of theta, right, which is what you need to actually define a metric, a local metric, like you want to define a local inner product, you can just write down the, typical inner product on the right-hand side. And you see that this M transpose inverse, M inverse, is giving you the inverse of the Riemannian metric, right? So beautiful. This way I can figure out I can integrate basically the curvature of space that I'm working on. And as you know, this e to the minus h is proportional to p, but I need one more correction. Right, I'm going to write down the Hamiltonian, the Riemannian Hamiltonian, and I know I can basically speak of the potential energy in the embedding, and I can actually know the kinetic energy as well. But of course, for the things to be correct, I have to think, take into account this Riemannian correction term. So people have. Oh yes, I'm sorry. It was okay. I'm very sorry. P is momentum, and I mean, sorry, that's an obvious mistake that I made. So P is actually M. I'm very sorry. That's very confusing. Yeah, so I should fix that. Thank you so much. Yes, this is M. Cool. Right, and then there's the Hamiltonian. That's called the Riemannian Hamiltonian. So now, I want to do the same thing, the stochastic gradient MCMC, but now I want to do the geodesic or the Riemannian version of this. And for that, people have shown, this is not our work, and you see the reference on the slide. The only thing that changes is the definition of D and the lambda. If you choose them in a very particular manner, then you can actually integrate this Riemannian metric. Okay. So now, if I write down the differential equations corresponding to theta and M or P, sorry for this awful confusion. Even though these equations look a little big, they are really nothing to be scared of. So here, let me start from the momentum, because this is just the same. This one, instead of M, now we have G inverse. So this is almost the same. But the other one is now including a correction term, like the typical gradient of the potential energy, the correction term, and a choice of a momentum, the kinetic energy, which is now defined through the metric, and a noise term, because this is a stochastic differential equation, right? And that should also be related, of course, to the metric, and that is captured in M as well. Right, and here, of course, the gradient is actually the gradient of the embedded posterior. So tilde means in the embedding. Good. So if we analyze this SDE in the noise-free regime and also friction-free regime, we just simplify this equation to look like that. And just you see, just like the momentum is really like looking like the Hamiltonian already, and the other one is just a integration over the momentum variable. So what you see here is if you discretize this, okay, and it's like a very typical thing, an earlier discretization, you are going to end up with, I don't know if any of you would recognize these things, but this is going to give me a Riemannian gradient descent with momentum now. Okay, and in particular, there will be two components. Actually, I should show you this in the next slide. There will be a geodesic flow, okay, which is, which I will call A now, this set of equations. And then there will be some friction term. You can ignore this, or you can take it into account. And then there is a projection onto the tangent space type of idea. So what we are having really is that we are computing a gradient, adding some noise to it, projecting it onto the tangent space of the current iterate, and then computing a geodesic flow, which takes both the point and the direction vector to the next point. Okay, and for example, for a sphere, if I were to discretize this, okay, then I just end up with very simple equations. So really, these are, just computable with a few lines of Python or MATLAB code. Yeah, and sphere is very useful also. And of course, by the way, people do this splitting, and splitting integrators is just, simplifying things. So instead of trying to simulate all at once, we simulate in an alternating fashion, either B first, O first, or A first, or ABOBA, or, there are other fancy integrators that you can derive from this. Now, instead of instead of momentum, if I forget about momentum now, right? In the earlier slides, we have recovered the typical gradient descent. Now I can do the same, and the variant, actually the stochastic variant, without the momentum variable, but taking into account the Riemannian metric, is called a stochastic gradient Riemannian Langevin Monte Carlo. It's a big fancy name for, rather simple thing, I would say. So, you can write down this equation in many, many different forms. This is one of the forms, but it's, I will show you how simple this can look. So basically, it's discretization. So here is your continuous version, and here is the Euler integrator, Euler Maruyama integrator applied, resulting in the algorithm you see on this slide. So I'm right now in the current iterate, theta, and I compute the gradient of the potential energy. And then I add a bit of noise on top of this. As you see, it's given by Z here. It's Brownian motion, Gaussian noise on top of it. And then I project onto the tangent space of that iterate. And that is really like a tangent, like in a current, if you know the manifold, it's easy to compute the tangent space. Sometimes you need more complicated stuff to compute it. But if you can compute, you can project on top of this plane. Now you have a direction vector, which is living in the tangent space of theta I. And you can apply your favorite retraction algorithm, which is a part of a geodesic flow. It's like an exponential map. It's just walking on the manifold, right? It's taking the point at theta I to, or theta k, to theta k plus 1, using the vector vk plus 1. That's what it does. And as doing so, it remains on the manifold, as maybe you see in this figure on the right. So there's a true geodesic here. If I have the exact exponential map, I would be walking on the true geodesic. But retractions, many forms of retractions exist. So first order approximations, for example, are acceptable, and they would be working. They will be walking on a different path, but still close, hopefully. Okay. Now, now this is our algorithm, basically. It's, I can either work with the Hamiltonian version or the Langevin version, doesn't really matter. It's a matter, it's a choice. Do I need to integrate momentum or not? Do I want to do something fancier or not? And now we can go on and look at interesting computer vision problems, such as synchronization. It's in computer vision. I will tell you how that looks like in a second. And solve a couple of those and see where this goes. So this idea of synchronizing things started with synchronizing time, obviously. And I have read this beautiful book on the topic called Einstein's Clocks and Poincaré's Maps. It's not a technical book, it's a history book. And it really talks about how, after standardization of the metric system, the standardization of time has evolved in Europe. There were a lot of fights around it. And actually, people had clocks, like local clocks, and they didn't know how to synchronize them. So underneath Paris, they have installed pneumatic air pipes. The whole underground of Paris was covered with this air pumping pipes. And really, the clocks were synchronized by sending air from a central clock to the local clocks. But of course, after the invention of the telegraph wires, people started using wires, and then the problem became really how can we, by checking the time between TA and TA prime, how can I synchronize the observer at time TA with the observer at TB here, or observer or at A and observer at B. Sorry. And first synchronization algorithms came from Einstein and Poincaré, and that's a fascinating read. And then, of course, many things happened. Now we use synchronization in computer vision as well, or in many other parts of machine vision, I would say, or machine learning. And I think we also have a lot of interest or overlap in terms of research with the people in the group, so that's always interesting. Now, the idea is we make certain measurements in a multi-view setup in computer vision, right? Most of the vision problems, you actually have, you actually observe, you actually capture many images. And of course, it's very hard to work with all the images at once. So what we do is a simplification. We isolate two cameras or two entities or two images, and then compute some kind of a map between those two data points in isolation. And of course, estimation techniques are noisy, so there's an independent noise acting on this estimate, pairwise estimate. And now, given a bunch of noisy pairwise estimates, we would like to recover some absolute information, which is a, let's say, or a unary information, if you want, an information per camera here, or an information per image. This could be the camera pose, or this could be the order of the points, for example, in a given image, right? So let's take a look. Let's start with the motion, for example. Let's assume that I want to recover the motion of all the cameras that were looking into the scene. I can always explain motion using some rotations and translations. It's a rigid motion of a camera in the end, and any point in 3D space can be acted on by elements of this group to yield another point in space, right? And usually people characterize rotations as 3x3 matrices. Here I write the general definition, but it's an orthonormal matrix with a determinant 1. Okay, so determinant -1 would have been a reflection. And this can either do, of course, coordinate transformation, so I can relate the orientation of the coordinates, or objects, so cameras also. And there are many representations of the same group, or parametrizations of the same group. Euler angles, quaternions, and the local algebras, and so on, are always possible. In this work, we use quaternions, okay, because they were simple enough to work with, and I can directly define a probability distribution on them. So let us write in a very general way what I've shown you in a while ago. So this is the map estimate. So this is more like writing it in a more generative way, but you can really take this with all the simplicity you want. So we define a probability distribution so I want to maximize over Q and T, right? So I define P of Qij, which is the given data, the relative poses, conditioned on Qt, okay? So I write this, so it's like a generative. So if I were to give you the absolute poses of the camera, how likely would this pairwise observation be? And I can do this for rotations, for quaternions, and for translations, for which we use Gaussian distributions because these are in Euclidean space. And I can assume some kind of a prior on the quaternions and translations individually. I can write this. This is a map estimate, obviously. With this maximization, I am not characterizing the distribution, full posterior, but to characterize a full posterior, I need to write it down, in the way you see here, and actually draw samples from it. And it's this whole framework that I've just introduced will be very useful. But before that, let me tell you that for the choices of distributions or rotations, we pick Bingham distributions. Okay, and this is basically like a Gaussian distribution on the sphere, but it is antipodally symmetric. So two sides of the sphere are assigned the same PDF value. Yeah, so it's basically like assume that just look, if you look at this equation, this V lambda V transpose would look like a covariance matrix if we were in the typical scenario of Gaussians. But here, instead of that, I am writing down the eigen decomposition on that point, very point on the sphere. And this is characterizing different, or this allows me to quantify the uncertainty in different x's, and that those different x's are dictated by V here. Okay, so that's a common choice for rotations, right? And now I would like to estimate the absolute poses of these cameras, right? And as I said, we can think of this as a graph. And here, if I want to do a cycle minimization, so if I want to satisfy, I want to ensure that all the cycles are consistent or all the cycles are null cycles. Like if I start from one node and trace a cycle, I come back to the same point. That is equivalent. If I have a group structure, that is equivalent to writing, to ensuring that for each MJ and MI, the equation you see here holds. And MJ and MI here are motion matrices. So it's rotation and translation composed. So we are trying to figure out MI and MJs given MIJ. That's basically it. And we just do run the same algorithm. We compute the gradient, and then we run the BOA steps on the quaternion manifold instead of the sphere, as you would see here. For rotations and for translations individually, this is how we do it. And just keep doing that, right? And what is interesting, I would like to show you one thing. Let me go back just a little bit. What is interesting in this, so this is the algorithm more or less that we are running. And here, if I choose beta to be 0, I immediately recover the Riemannian gradient descent optimizer. Or if I use the Hamiltonian, I would recover gradient descent with momentum. And for finite choices of beta, I am having a Riemannian sampler. Okay, so I can, if I want to, I can just immediately converge near the point that I would like to sample from, and then set beta, this temperature parameter, to a finite value and just start sampling around it. So, and that's what we exactly do here to quantify uncertainty. And this is how the optimization would look like. Yeah, more or less it converges. And then, because now we have multiple solutions, and when I say solution, it means all the poses of all the cameras. So we multiply solve this synchronization problem to get sets of poses. And for each one, I can reconstruct the scene now. And from this reconstruction, I can start assigning uncertainty values individually to each point. Okay. And as you see, whenever I have more views, it's more confident. Whenever I have less views about a structure, I'm less confident. And same happens for distant things. The nearby structures are more confident, and faraway structures are less confident, more uncertainty. So now we can actually go from synchronization of poses and rotations and translations to synchronizing correspondences between shapes or images. That's also fine, doable. And when you think of this, you should actually think that correspondences can be, at least sometimes, can be written down as permutation matrices. And the permutation matrices are the vertices of what is called the Birkhoff polytope. And the Birkhoff polytope itself is nothing but the manifold of double stochastic matrices. Okay, so every point on each face here would look like a doubly stochastic matrix. And of course, we are interested in recovering permutation-like things, which are lying at the vertices, and they are binary. Good. So for that, yes, we are looking for permutations. I can write the same cycle consistency instead of rotations in this manner. And now I am not explicitly probabilistically modeling rotations, but I'm directly writing down the energy. And then this probability distribution will be induced by Boltzmann distribution, for example. And we can relax this to the double stochastic matrices. And the manifold of double stochastic matrices have been recently characterized in 2018. And then I can use the Riemannian operators of that manifold to do this, to minimize this energy. At the same time, I can use my samplers to quantify the uncertainty, so to come up with a Bayesian estimate. Right? And if you look here, I can estimate correspondences. Starting from an initialization, I can go to a better solution. But at the same time, I can come up with a confidence map. And if I had an oracle to pick the high values from this confidence map, you see that it's becoming diagonally dominant, which is the ground truth solution here. And if I look at it, take the second best observation, for example, then I can start recovering even better solutions. That's a Willow garage data set that we tried it on, and somehow worked well. Okay, so I must ask, do I have some time, or should I stop here for taking some questions, because this is what I wanted to cover, or if I have time, I would like to give you a very, very simple, very short overview of another very related idea.
So I think, because okay, we can wait half a minute and see if anyone has an important question to ask, and if not, you can give the bonuses.
Okay.
So people in the audience, if you have questions, just type them in the question and answer box. Yeah, so yeah, you can give us the bonuses.
Good. So I like, this is the typical rotation synchronization problem that I just introduced. Basically like like a motion type of matrix that you see here, and I'm trying to recover the absolute motions, which is denoted by the red matrices. I mean, and here I'm really talking about rotation synchronization. I'm for a second ignoring the translation part. And very sorry. But now, sometimes when we capture images, because of self-occlusions or symmetric objects or self-similarities, we cannot really distinguish an exact camera pose. We should not be, because it's really uncertain. Now, in this example, for example, if you see the handle of the cup, then you have a great idea of the pose of the object. But when you don't exactly know, right? So there are symmetries somehow. And now we like to factor that in, and eventually between pairwise estimations, instead of having only single one or only single rotation as a pairwise edge, I can have a full distribution on the rotation space if I can estimate this. Let's say there's a magical pairwise pose estimation algorithm that is giving you such distributions, and they are empirical, right? I'm just sampling, maybe like 10 or 15 rotations or 40 rotations, and then looking at the rotation sphere, as you see here, and that there's like something like a kernel density estimate on the manifold, right? So now, how would you do synchronization? Like come up with all the full distribution of the poses, given such distributions on the edges. Right. So now your edges are labeled with probability distributions on rotations, and you would like to recover probability measures on the nodes. Well, we are working with empirical measures on manifolds, and while the classical rotation synchronization you see here is just like the typical thing before, our measure synchronization is different, because now we need, instead of computing distances between rotation matrices, we need to estimate divergences between probability distributions on rotation spaces. So you see here that given two measures, two absolute measures, from them I can compute a relative measure by composition of measures, and then I have the observed relative rotation or distribution on observed relative rotations, right? And then I can compute a divergence between these two probability measures. And well, while the typical optimization looks like on the left, that doesn't give you uncertainty, and that doesn't take into account the uncertainty on the edges. I can have I can have some kind of a Riemannian measure synchronization, which is trying to ensure that the distributions are the same, right? And I'm trying to directly optimize for all the probability distributions on all the nodes. And for that, as a divergence, in the paper, we pick synchron divergences or maximum mean discrepancy like measures or distances. And then we benefit from recent optimization, global optimization algorithms to minimize it. Good. And in the second part, I just want to mention, it's like an invitation, maybe rather. If you look at the recent diffusion models, they also do sampling with Langevin, right? And now you have maybe, I don't know, maybe most of you knew this stuff, but maybe you have a better idea about what this means. And it's just a Langevin diffusion, and here the gradient of the data density is learned, and that's the difference, right? The other parts are just the same. So now, how would you improve these things, right? So we can do Hamiltonians, we can have Riemannian diffusion, right? And in fact, people have done it. People have proposed Riemannian diffusion models. And for example, inferring stuff or inferring quantities on Earth, like weather prediction or, natural disaster prediction and things like that. Right. Good. So, I mean, my talk is more or less ends here, but a couple of messages that I want to give. This is basically like a cooking recipe for MCMC methods. So you can have access. I mean, I have a full course on this, around these topics in Stanford. And those slides are actually online. Maybe not the most recent ones, but definitely many of these slides and more of that is online. And I will be very happy to share this link with you. Good. So we have a parameter space on the manifold, okay, and then we have a potential energy that is defined on these parameters, theta. Okay. Now we can have access to the gradient here, right? But that's, you know, that's a function on the manifold, so it's a little interesting to speak of the gradients. But if we consider the Hausdorff measure, you know, the posterior is given with respect to the Hausdorff measure because it's living on a manifold, right? And we do the trick of embedding it. So we basically say I'm going to have an embedding function, like a chart, which goes from, or parameterization, which goes from the Euclidean space, the local Euclidean space, to the manifold, right? And then in the embedded space, I can consider a Lebesgue measure now, and write the embedded posterior, and define my gradients in the embedded posterior. And then I know my relationship. I know that the Lebesgue measure, or the posterior, and the Hausdorff are related by the magnitude of the gradient here, right? And then I can choose my favorite SDE. It could be Hamiltonian, it could be Langevin, and so on. And of course, depending on the choice, I can write down either the Hamiltonian or the corresponding Langevin potential. And then I write down the corresponding differential equations given by the Riemannian metric here, right? So this is the only modification. And the Riemannian correction term, the lambda here, comes from the log G that you see in the middle. And then I can, of course, choose my favorite integrator, Euler-Maruyama, and just write down the general algorithm, because the discretization of that is going to give me the algorithm immediately. And if I simulate this, you know, by injecting noise and stuff, then I will be drawing samples from the posterior defined on the manifold. So that's all I wanted to share. And you know, this and openly invite a little bit, you know, towards this, towards using these methods more in conjunction with the modern deep learning techniques. Yeah. So thanks.
Yeah, thanks a lot for a really great talk. Very, very interesting. It's kind of about time, so unless someone has a very important question, you may end it. I do have some questions I can follow with you afterwards.
Yes, please.
Yeah, so yeah, thank you very much.
Thank you. So if you have questions, let me just stay for a minute.
Sure.
Oh yes, so I can basically, so I had the link in the beginning of the slides.
Thank you.
And Georgia,
Okay,
you stopped the recording, right?
Yes.
Okay, thank you.
Okay, so yeah. Sorry to scroll through these. Yeah, so the link is here. So if you just want to immediately check it. But I can also share this link. Or let me just, can I send things in the chat
Sure.
or not?
Yeah.